Hello, my name is Rahim Rezaiha, and in this tutorial we're going to demonstrate how to do CFD simulations of flow around the convergent-divergent duct, which is typically used to accelerate the flow for wind energy harvesting applications. So after this lecture, you'll be able to create a geometry of a convergent-divergent duct and the surrounding computational domain using ANSYS Design Modeler, decompose the domain to facilitate the grid generation, generate a hybrid grid with bound layer grid along the duct walls using ANSYS meshing, prepare the simulation settings in ANSYS Fluent, and do a preliminary post-processing, and arrange everything within the ANSYS Workbench environment. So we'll start with an introduction to the problem, and then we'll go through the details of the grid generation, geometry creation, grid generation, simulation settings, and then post-processing. So the first part, the introduction to the problem. So CFD is typically used to design and optimize the ducted wind turbines. So the duct itself and the wind turbine itself. It can be a decoupled analysis of the duct and the wind turbine, or a coupled analysis including the duct and the turbine. It can be used. The result can be used for aerodynamic or aeroacoustic analysis. So here, for example, you see two different ducted wind turbines, but one with the Windtimer, the company, and the other one a research project by the Kyushu University. And how does it work? So the flow comes from left, and then there's a conversion section which accelerates the flow. And then there's a throat, typically with a constant diameter, where the turbine is located to extract the energy. And then there's a diversion section to bring back the pressure to the atmospheric level. And sometimes a flange is also installed to further help the performance of the duct. So in this tutorial, the duct that we're going to simulate has a diameter of 1 meter, so a radius of 0.5 meter. The conversion part, the nozzle, has a length of 0.5 meter, one radius with an angle of 20 degrees. The throat has a length of 0.5 meter, also one radius. And the diffuser has a length of 3 meter, so 3 diameter, and with an angle of 5 degrees. So here you see the 3D schematic of the duct that we're going to simulate. So the nozzle section with 20 degrees angle and 0.5 meter length. The throat with 0.5 meter length, and here we also see the radius. So this is the 2D view, and then the diffuser with 5 degrees angle and 3 meter length. So in this tutorial, we're going to simulate this duct using 2D axisymmetric simulations. So therefore, we'll create a 2D domain, and inside the simulation software, we're going to define it as a 2D axisymmetric case. So the computational domain around the duct is shown here. So from the throat beginning, we have 10 diameter, so 10 meter to the domain inlet, 20 diameter, just 20 meter to the domain outlet, and the domain width is 10 meter. So we're going to create a hybrid grid, so structured grid in the surrounding domain and unstructured grid with bound layer grid along the duct walls in the duct region with local refinement in that region. So here you see the different regions of the domain, so the whole domain. And so this is the structured part and unstructured part, and then the duct wall with local refinement and the bound layer grid along the duct wall. So after the introduction, we will start with the details of the geometry creation. In this part of the tutorial, we're going to demonstrate how to create the geometry for a 2D axisymmetric simulation, CFD simulation of a convergent-divergent duct for wind energy harvesting applications. So this is the ANSYS workbench environment. We'll be using the fluid flow analysis system. So I have already opened the fluid flow analysis system, and to create the geometry, we will be using the software ANSYS Design Modeler. I also already opened the software, so we have it open here. So we're going to start. We select the XY plane for the base sketch, and then we make the view normal to the XY plane. We create a new sketch, and then we move to the sketching panel. So as already mentioned, we're going to create a 2D domain that later in ANSYS Fluent will be treated as a 2D axisymmetric domain for the CFD simulation. So then what we need is a set of lines. So the first one, you start from the y-axis to create a line parallel to the x-axis to represent the throat of the duct. So I go horizontally, I release the button, and then I set the dimensions. So as already mentioned, the length of the throat is half a meter, so it's equal to the radius of the throat. So we put the dimension as half a meter, 0.5 meter. So I zoom to fit. Okay, so this is the throat that we have, and then so we also need to set the correct location to the axis, to correct distance to the axis. That will later be the radius of the duct. So we select the throat, and then we select also the axis, the x-axis, and then here we also set the 0.5 meter. So this will ensure that because the simulation is to the axis symmetric, so the distance from the throat to the axis is half a meter. So this makes the diameter of the throat 1 meter. So I move a bit the dimensions so that we make the feet a bit better. Okay, so this is now the throat. So now we're going to create the convergence section of the duct, which makes the nozzle. So I go to the point when I see the letter P, and then I draw a line with an arbitrary dimension. Later on, we'll set the dimension. So the distance, the horizontal length of the convergence section is also half a meter, so 1 radius of the duct. So I also set the correct dimension for that. And then the angle is 20 degrees. So we select from the dimensions the angle, and then we go counterclockwise to select the line. So first this line, and then the axis, and then here we can set the angle as 20 degrees. So this is also correctly set. So we have the correct dimensions for the conversion part. Now we go to create the divergent part. So again, we are going to create a line. So we go from the letter P, and then we create a divergent section, and then we're going to set the dimensions for this section. The horizontal the horizontal length of this section is going to be 3 meters, so 3 times the diameter. So I want to set it as 3 meters. And then the angle will be 5 5 degrees. So we go again counterclockwise. So we first select the axis and then sorry, I have to select the angle. So we select the axis and then the divergent line, and then we set the angle as 5 degrees. Okay, so we also have now the divergent section. Now this is the inner wall of the duct. We're just going to make a copy of that and also create the outer wall. So I select the 3 lines with Ctrl C and Ctrl V. We have set another line, and then I just put it a bit higher and then press escape so that I stop with this operation. So again, adjust a bit the dimensions. So this one I bring it down, and this one I put it. Okay, so this is okay. But this one I want to put it a bit outside. This one can also come inside. This one can also come inside, and this one I put it here. Okay, now it's correct. Now we want to set the thickness of the duct wall, so the distance between the upper part, the outer part, the wall, and the inner wall. So I set a vertical distance between these two walls, and then I set it as 2 centimeters, 0.02. And then you see that all the walls are now correctly positioned. So what we need is to close this 2 walls. So I need an extra line here and another extra line here. Okay, now the sketch is ready. The sketch of the duct is ready. Now we move to the modeling panel, and then we create a surface from the sketch. And then we change the operation to add frozen and then generate. So now we have the duct wall. Now we're going to create the computational domain around that. So on the same XY plane, we create a new sketch. And then I go to the sketching panel, and then I create a big rectangle. I will set the dimensions. So the width of the domain, we want it to be, as already shown, 10 meters. So let's set it as 10 meters. The horizontal distance from the domain inlet to the throat, we want to set it also as 10 meters. And then the downstream distance from the throat location also to the outlet of the domain, we set it as 20 meters. So the downstream part of the duct. Okay. Now this is the computational. This makes the computational domain. We come back to the modeling panel, and we also make a surface out of that. Okay, we also have a surface. Now we need an extra region near the duct so that we can refine the grid. So we create a new sketch, sketch 3. We go to the sketching panel, and similarly we create a rectangle. And then we set the dimensions of the rectangle as with a width of 2 meters and with an upstream distance of also 2 meters and with a downstream distance of 5 meters. Okay, so this is also correctly set. We go to the modeling panel, and we also make a surface out of this sketch, and then we generate the geometry. Now we have to project this smaller rectangle on the bigger rectangle so that we make them separate surfaces. So we do this by the Boolean operation and by the use of subtract. So the target body will be the big rectangle and the tool body will be the smaller rectangle, and then we're going to preserve the smaller rectangle. And then we click on generate. Now we can see that we have this part or this body, and we also have the smaller one. Now, because we're going to simulate the flow around the duct, we're going to subtract the duct itself from this smaller rectangle. So we do it again with the Boolean operation. This time the target body is the smaller rectangle, the tool body is the duct, and then we're not gonna preserve the duct. So we click on generate. If we zoom in, we see that we have a hollow region here. Okay, so we created the computational domain, the big computational domain, the refinement region, and the geometry of the duct. So we have them all here. So I just rename this as duct region, and then this can be a rest. And then in order to create conformal grid, so with connecting nodes between these two zones or these two surfaces, we need to put them in one part. I also put this as put a name for this part, and then we have two bodies inside one part. So remember, we want to change them to fluid, and again, to make the conformal grid happening, we have to change the shared topology to automatic. Okay, so this is also correctly set. Now we need a bit of divisions in the domain to facilitate the fully structured grid in the outer domain. So I have to project these two lines on the upper edge. Okay, now you see that it's divided into three parts. Now we also want to project this two. We can do it by one, so we project one of these edges, one of these points on this edge to also split it, and then we also project this point on the other edge. So now the edges are decomposed. Now we want to create some lines for the domain decomposition. Okay, so we go to tool, concept, lines from points, and then we change it to add frozen. So now we have two lines here. Now we can select the other points. So to here and to here, and then you go lines from points, add frozen, and then we also have these lines or edges, and then we should select 4 of them, and then go to tools, projection, and then project these 4 edges on this face, and then this will divide the face into 4 parts. So now we no longer need these line bodies, so we suppress them. We only have 2 surfaces. Now we only need to set the boundary conditions. So the 2 bodies, we name them as fluid. So okay, this is set. Now these 2 edges will be the inlet of the domain. Okay, and these 2 will be the outlet of the domain. Okay, and now we have 3 edges for the symmetry conditions on the top. So this is symmetry, and then we have these 3 edges for the axis. Name it as axis. And now we have the edges of the duct, and we have to set them as walls. So we selected in total 8 edges, and we select them as duct and wall. Okay, now we save the project. Save project. And this was the end of the geometry creation. Now we can close the design modeler, and then we see that we have the green tick here, so the geometry is ready, and now we are ready to go for the grid generation in the next part of the tutorial.